Hi. In this lesson, I'm going to talk about 4.1 anti-differentiation. There's two big parts of calculus. One is differentiation, which we've been doing a lot of. And we saw that differentiation we can do implicit, and we can do different word problems and so on. The second is integration. Integration is solving word problems also a different way, and also finding areas and volumes and things like this. And one of the big parts of integration is anti-differentiation. So anti-differentiation, as the name would imply, is the reverse of differentiating. In other words, if you had a problem and you knew the derivative of it, let's say we had y equals x squared. What is the derivative? Well, y prime is equal to 2x, right? When we do an integration, we show by this symbol right here, the integral. This is called the integral. So we're doing the integration or the anti-differentiation of 2x. We usually put something like dx behind it, and we'll explain that a little bit later. But right now, just concentrate on the 2x. And what will happen when we take the integral of this, it's going to become equal to x squared. It's going to give us the original problem back. We're going to put our first derivative in there, and it's going to give us back the original problem. And the only problem is if the integration, if this had a value of a number, we don't know what that number might be. This might have been an x squared plus 7 or something like that. When we took the integral of that, that 7 became a 0. So when we take the integration of it, we know that there might have been some number. It might have been a number or not. So we just put plus c, indicating there might be some constant. Okay. This is called an indefinite integral, in that we don't know what that number is. And then we're going to do something with a more definite integral, that we have definite boundaries and so on, restrictions on it. But right now, we're just kind of looking at this basic idea. I'm going to move this down just a little bit. Okay, so let's take a look at some of the basic rules. And just remember that this is the reverse of differentiating. So let's start out with one here. I'll give you an example, and then I'll give you the rule. Probably be easier. Say we want to take the integral of 3 dx. We have a number, and we want to take the integral of it. Well, because we're doing the reverse, notice when we did the reverse of 2x, it became x squared. It got larger. So when we do the integral of a number here, we're going to put an x behind it. And it may have had some number, so we don't know. We're going to call that 3x plus c. So when we take the integral of a constant, and this is indicating we're taking the integral of it, the integral of a constant would be the constant times x plus some number. That would be the general formula. Okay, well, let's say we had something, the integral of x squared dx. What was the actual problem? Okay, so I'm going to show you what the integral would be. It'd be x to the third over 3 plus c. If we took the integral of that, we'd end up with 3x squared. If we took the derivative, we'd end up with 3x squared over 3, and the 3's would cancel, so we'd end up with x squared. So what do we do to this? Let me write it out here. When we have x to some power, it could be any power, 2, half, whatever. Remember when we differentiated it, we subtracted 1. If we had, say we had x to the cubed over 3. What we did is we multiplied the 3. We used the power rule, put the 3 in front. And then we wrote this as x squared, and then we put it over whatever was there and canceled them off. Okay, we're doing the reverse. So if we have x to the n dx, what we're going to do is we're going to add 1 to the power, and then we're going to put it over that number plus 1, plus c. So we're going to add 1 to the power, which gave us 3, and then we're going to put it over 3. We're going to just do the reverse. Instead of subtracting 1, we're going to add 1. But we have to put it over that same number, just like this problem. Okay. Another one that comes up is, say we want to take the integral of 1 over x dx. This has a definite answer. The answer to this is the natural log of x plus c. The integral of 1 over x dx is the natural log of x plus c. Okay, what if we had the integral of e to the 2x dx? Something with e in it. This is equal to e to the 2x. It's equal to itself, but it's kind of like the chain rule over 2. The integral of e to some number in front, a stands for a number in front of x, we could have even said n, is equal to 1 over a times e to the whatever it was, ax plus c. So those are the basic rules, and we'll go through some problems, working them out and trying to figure these out. They're in your book on 391. You want to go through them, but we'll do some problems here. So we're going to grab some just right out of the book. Let's try example 1. We've got 8 dx. Sometimes when we have an integral of a constant, we move the constant outside of the integral. The integral of just dx is x. And then we just proceed to put that 8 in front of it. So when we have a constant in front of dx, we remove the constant, we move it out, this 8 stays, and then the integral of dx is 8x. And you could put it to the 1 over 1, but no sense in doing that, plus c. You kind of want to remember the c. It reminds me of a joke. These two guys, two mathematicians were in this restaurant drinking coffee, and they were working on this long, complicated calculus problem. And the waitress came up to them and said, "Do you want some more coffee?" And they shoved her away, saying, No, we're too busy. We're too busy trying to solve this problem." And they kept working this problem, and she'd come back a couple of times and get away, we're too busy. They didn't have any time for her. So when they finally finished, they called her over and said, we want some more coffee. How come you haven't offered us any, or something like that? They were kind of rude to her. And so she looked at their answer, and she said, "Well, that's pretty good on your calculus problem, but you're wrong." And they looked at her stunned, like they've been working for this for half an hour. They said, "What's wrong with it?" She said, "You forgot the C." So I don't know if it's funny or not, but that's the problem. Okay, let's try another one here. 3x squared dx. Well, let's move that 3 out. We got x squared. What's the derivative of x squared? This would be 3, And we're going to add 1 to the power and then put it over 3. Whatever power you have here, or whatever exponent, you're going to put it over the same thing. And of course, that's going to simplify to just x cubed plus c. So remove the 3, then take the derivative of x squared, which is x cubed over 3, and then cancel it out. So it's a little bit harder because you're used to subtracting. See, this normally, if you took the derivative, this would be just of 3x squared. It would be 3 times 2 is 6x, and then take away 1 for the power, it would have been 6x. But we're not taking the derivative, we're taking the antiderivative. Here's another one. The antiderivative of e to the x is e to the x plus c. So that's an easy one. That's why we like to use e to the x. What's the derivative of e to the x? E to the x. So it works both ways. And the antiderivative of 1 over x dx is simply the natural log of x plus c. So this one's a little harder to recognize. Okay, well, let me show you a little variation on this one. Well, I will in just a second. Let's go through example 3, example 2, and then we do example 3. So what if I add the integral of x to the 4th dx? This is example 2. What would that be? Well, it's going to be x to the 4 plus 1 over that same number, 5, plus c. Just that easy. And I suppose, sometimes they write it as 1/5 x to the 5 over c. I usually just write it like this because it's easier to kind of remember. But either answer would be okay. Okay, let's do some more of those. X to the 7 dx is x to the 8 over 8 plus c. Pretty cool. Okay. X to the 99 dx. X to the 100 over 100 plus c. Well, here's a little bit harder one, excuse me. The integral of the square root of x dx. Well, in this case, what we want to do is we want to write this, first of all, with exponents. So that's going to be a half power, right? So we're going to add 1 to that. That's going to be plus 1, or another way of saying 1 would be 2 halves, 2 2s. So this is going to come out x to the 3 halves over 3 halves. Well, we don't want to write the problem that way. So what would that be? Just kind of expanding out, x to the 3 halves divided by 3 halves is x to the 3 halves times, when we divide by a fraction, we use the reciprocal, 2/3. So that equals 2x to the 3rd over 3 plus c. Well, that's a lot of work, isn't it? We got this as 3 halves over 3 halves, and we have to get rid of the 3 halves, so we have to use the reciprocal, then we have to multiply. So what we usually do on a problem like this is when we write it over here, we do change it to a fraction. Okay, so we think of it, I put it down below it, is that this is going to be plus 1. We don't usually write it x to the 1.5. You could think that 1.5, which would be 3 halves. But instead of putting it over 3 halves, we just multiply it by its reciprocal, because that's what happened here. We ended up multiplying by the reciprocal of 3 halves. So we just take this 3 halves and put it as 2/3 plus c. That way we don't have to go through all this brain work. We can do it much quicker. So we just, if it has a fractional exponent, just use the reciprocal. If this was 4/3, use 3/4 there. Okay. Here's another one. 1 over x cubed dx. Well, you might think to yourself, okay, wait a minute here. 1 over x dx is ln x. Would this be ln x cubed? Well, it might be a good guess, but it's wrong. Okay. Instead, what we do, we only do this if it is exactly 1 over x, or 2 over x, or 3 over x. But we just have to have an x on the bottom. If we have like an x cubed, we bring it up to the top. This is still a derivative, antiderivative, or you can call it an antiderivative or an integral. So we have the integral x to the -3. We're going to add 1. So that would be x to the -3 plus 1. What would that give me? That would be -2 over -2. See, plus c. Or we can move it down to the bottom and say this is 1 over -2x squared plus c, which would probably be a little bit nicer answer, huh? So that's what we are going to do with that one. Yeah. Okay, so you get the idea of these integrals. That's pretty amazing. Can we do, we're only doing singles. What if we wanted to do something that's multiple? Like we want to take the integral of 3x to the 5th plus 7x squared plus 8. This is example 5 in your book, dx. Well, we could, just like when we did the derivatives, take the derivative of each little part. And that's what we're doing today on this one. We usually don't write this out as thoroughly as I'm going to write it out, but you can kind of think this, that we're taking the derivative of this, and then we're taking the derivative of the second term, and then finding the derivative of the constant. So this would simply give us, could factor out the 3, and then this would be x to the 6 over 6 plus, you could factor out the 7. That would be x to the 3rd over 3. See, we're just kind of not writing it down, but I'm taking this 3 out. I'm taking this 7 out. And I'm even going to take the 8 out. So this would be plus 8. And remember, dx is just x plus c. And then we would simplify. Here we got 3 6's, so we might want to simplify that to putting it over 2, or something like that, or a half, or whatever. You could write as x to the 6 over 2 plus 7x to the 3rd over 3, or you could write it as 7/3, plus 8x plus c. So normally we don't put this step in, but this is really what's happening. We're taking the integral of each part. Okay, the next problem was something that looked like this. Dx. Okay, so you might think we would write this as 1 over x times that, and then that would give us an ln x. And you could do it that way, but I think the easier way would be put each one of these terms over x. And then simplify them if you can. I'm going to put a parentheses here, dx, and we're going to put a, it's not really, it's a symbol like that. Okay, then what we could do is simplify these. Well, let's just look at this one. The x's would cancel. This should have been over x, and the x would cancel here, x to the 3rd. So we got 4 over x plus 3. The x is canceled out, plus 3 plus 2x cubed. Okay, maybe I should write that as a separate step so you can see. It's kind of messy. Now we're going to take it, well, remember, this is an ln x. This is x. If it's x to a power, then we bring it up. But if it's just x, this is going to be, the 4 is going to stay. We can move the 4 out. So it's 4 ln x plus, this is just 3, but we have to add an x. It's getting larger. See, when we're integrating, they're getting bigger. Plus 2, we're going to factor out the 2. We're not going to multiply. This is x to the 4 over 4 dx. So we factor out the 2, the 3, and the 4. Now let's see if we can simplify just a little bit more. Plus 3x plus, we can reduce this to x to the 4th over 2. And we don't want to write a dx here. That was my mistake. Plus c. That's what we want to put there. Kind of tells us we're done. And there might be some constant, but we don't, it could have been a 7 or 2 or 3. And so that's basically the idea behind it. Okay. On example 6, I think this is getting a little bit ahead of ourselves, when we have something like this. Maybe not too much. Let's take a look at this one. Function of x equals integral of 2x plus 3 dx. Okay, so the way I would do this one is, I might think of these as two separate problems, or just remember that I'm going to take the integral of 2x, I'm going to factor out the 2. This would be x squared over 2 plus 3x plus c. So this gives me 2, this first term gives me, I factor out the 2, and that gives me x to the second, because the power was 1 over 2. This had no, I factored out the 3, got the dx, x. And then I could reduce it to x squared plus 3x plus c. So yeah, you could do it. So that's all there is to it. We don't want to do a whole lot of things, which you can do quite a few of those. Okay. And that's pretty much the idea behind it. Okay, so on the next page, there's lots of these to practice, and you want to do as many of these as you can, just so you're getting used to it. Here's one that's a little confusing. Just looked at number 17, dx over x to the 4th. Sometimes when you're doing a problem like this, you want to kind of rewrite it a little bit so it makes sense. Might look like ln x. Every time I see an x on the bottom, I'm thinking ln x, but it's not really ln x. So on this one, we're going to bring it up. dx. Okay. I'm going to add 1 to the power. So that's going to give me -3. Remember, instead of subtracting, I'm adding 1. So that would give me -3 over -3 plus c. Or I could write it, if I wanted to, I can move this down to the bottom and maybe keep the negative on top. So this would be, I think I might have enough room here, -1, 3x cubed plus c, like that. So, or a -1/3 or whatever. I would probably write it like that. How about this one? Here's an interesting 121. And sometimes when the problem is kind of complicated like this, you have a parentheses or something, sometimes we do write it as two separate integrals. Just put a dx here like you're distributing, plus this integral, 5 over x squared dx. Sometimes it's easier, okay, break it apart and do each part. This looks like it's going to be, this is the same thing as, let's factor out this 3, and then that gives us 1 over x. So this is 3 ln x. See, take this 3 out of there. And this one, let's do the same thing. Let's bring the 5 out. But now we have the integral. We took the 5 out, but we have the integral of 1 over x squared. So this one we would bring up to the top. So we have 3 ln x plus 5 times, and then we're going to add 1. Remember, we're adding 1 x to the negative 1 over negative 1. So, you might not put as many steps as I'm doing, but this would become negative 5. So we could write this as minus 5, and then we could bring the x to the negative 1 down, and it just becomes negative 5x plus c. I guess I should have put it there, plus c. So, it's getting used to it. It's not all that easy. 3 ln x. Now, on this particular one, what they did in the back of the book, they just simply wrote it as, they divided this by negative 5 by the 1. They wrote it as negative 5 x to the negative 1 plus c. So sometimes they write it with positive exponents. I was taught when I took calculus many years ago, if the problem had started out with a fraction, it should end up with a fraction. But nowadays, things have changed. We're now in the 21st century, and we're not using horse and buggies and things like that. So apparently they changed calculus a little bit along with the times. And so we have this type of thing. So anyhow, I hope you enjoyed this. Work on these problems and see what you can do. And if you have questions on them, I can answer them, and you can text me or ask for a live Zoom or whatever. But try them, and it's going to be a little bit of adjustment period because now you just learned derivatives. Now you got to do just the opposite of the derivatives. Instead of adding, instead of subtracting, you're adding, and you're getting used to it. And of course, then there's more stuff that we have to learn, and applications to these things, and all kinds of fun stuff coming up. So, these can get pretty difficult because right now we're just working some basic ones with addition. What happens when we have to use, find the antiderivative of something where we use chain rule, or where we used ABBA, or where we use BABS? Those problems can become kind of difficult for us to do. So give it your best shot, see what you can do.